So hello everyone, we'll be discussing about the boundary value problem formulation in this chapter and perhaps also discuss some of the solution strategies which are commonly used to solve those problems. Now, one of the first things which we would want to mention over here is that we want to first define what the problem of elasticity is, and then to formulate in a way that we can actually solve it. So let's see what do we mean by problem and formulating it. So let's summarize what we have done until now. We have developed some equations, or the so-called field equations of elasticity, and they are mostly differential equations which relate the stresses and the strains and the displacements within a certain solid which we are trying to study. Now in this case we want to consider the last part of the problem, which is the boundary conditions. Okay, so we have always been telling all this while that if a loading is applied, deformation is there, or internal forces develop and so on, but this is the time where we'll be very specific about what the boundary conditions are. Okay, and that's where we want to head in this particular discussion. So, and knowing a boundary condition is definitely not an option, it's a necessity, because unless you know what the boundary conditions are, whether the boundary is allowed to move, whether what forces or temperature loading are applied on the boundary, we would not be able to tell what are the stresses and strains internal to a solid. Okay, so let's try to see how that works. So let's just summarize what all we have learned until now. We have learned about the strain displacement relation, that's Eij is half Ui comma j plus Uj comma I, and this is all valid at one specific point of a solid. Everything which we are writing over here is valid at say one specific point of the solid. Then the second was the compatibility equations, which ensured that for a given arbitrary strains, the displacements would be continuous and single valued. So this is what the compatibility equation were. Okay. We had seen that it is actually only 6 of them, and eventually only 3 of them are independent. The last, or the second last, was the equilibrium equation, which was essentially about the force and the moment balance, or the conservation of linear and angular equilibrium at this specific point. And hence, if every point was in equilibrium, the whole solid would have been in equilibrium. The last, or the sort of latest thing which we have learned about, is the Hooke's law for a linear elastic isotropic solid. There were two forms of it. One was sigma ij is equal to lambda e kk delta ij plus 2 mu eij, and eij is equal to 1 plus nu by e sigma ij minus nu by e sigma kk and delta ij. Okay, so this is the Hooke's law which we had for the linear elastic isotropic solid, and we had seen the derivation of it. Okay, so as we have seen that the compatibility equations will ensure that the displacement is continuous and single value and are only necessary when the strains are arbitrarily specified. If you have displacements which were given to you, then to find the strains you don't have to do that check, because if they are not continuous and single valued, you will not be able to do this differentiation to find the strains. So it's only when the strains are arbitrarily specified. Okay, so in discussing the equations of elasticity, this compatibility equations are normally set aside. Okay. The reason is that they are only needed when the strains are arbitrarily satisfied. Okay, so what are the general system of field equations? There are how many relations over here? There are six strain displacement relations. Okay, there are three equilibrium equations, and there are six Hooke's law equations. Okay, sigma ij will be like six independent components, and that's why. So you have a total of 15 relations which you have in front of you, and let's now define the so-called problem. The problem can be said to be able to find the displacement, the strain, the stress for a given material property lambda, mu, and the body forces or the body force density. Okay, so the problem of boundary value problem, so called, the starting point is that at any point of interest, say over here, you want to find the displacement, you want to find the strains, and you want to find the sigma ij, which is the stress, given the material properties lambda, mu is given, and the body force density is also given. Okay, so now you have how many unknowns? Let's see. You have three displacements, then you have six strains, and then you have six sigma ij's, which is the stresses. So you have 15 unknowns. Okay, so you had 15 field relations, this and this and this, and then you have 15 unknowns. So this is somewhat of a good thing for us, and now we'll see how the actual formulation can be done by including the boundary conditions. So it is a reassuring fact, as is given in your textbook, that the number of equation matches the number of unknowns to be determined. Okay, and we'll see how we can proceed with this. So let's now move to our next discussion, which is boundary conditions. So this, what I say, is called our problem. So you should remember this in, okay, what is given and what is to be found is contained in this. Now if you want to solve for this P, it requires boundary conditions to be known, and there are, for our case, mostly two types of boundary conditions. One is called the supported, and the other is called the loaded. This concept is shown in the diagram what I'll just draw over here. It's actually the same body, but I'm not able to replicate my own drawing. Okay, so let's call one as the traction. So S is the surface, R is the bulk, the other is the displacement condition. have this given displacement u, and the third situation can be that part of it which is SU, and the other part of it has the traction specified. This is ST. So this is called mixed conditions. Okay. So there are three basic categories, and it is needless to say that S will be equal to ST plus SU. SU is the part where the displacements or the support is specified, and ST is the part where the loading or the traction is specified. Okay. Now, one of the important things which we should mention and perhaps demonstrate is that a statement from our text that it is generally not possible to specify completely both displacements and tractions at the same boundary point. It is possible to prescribe part of the displacement and part of the traction. So this is a situation which we'll see in slightly greater detail, but I'll tell you what is allowed and what is not allowed. Say if this is the boundary and you have like your x and y in this form, if this is the boundary point under consideration, this is the boundary point, okay, you can have ux specified, and you can have the tn x specified, sorry, tn of y specified, which is the solid is over here. This is possible. You can have tx traction at this point specified, n represents obviously the outward normal because the traction requires an outward normal, and you can have the uy specified, but you cannot have ux specified and txn specified, or you cannot have tny specified and uy specified. Okay, this is not allowed. So this is what it means, that part of it of traction, part of displacement can be specified, but the parts have to be like this, not in the same direction. Okay, so this is what we can have allowed. So let's see an example of how this plays out. Let's see a situation like this. This is a solid, and then there you have a symmetry line. Okay, and then you take half of it over here. So let me just draw. Because of the symmetry, we can consider one half of it. Loading applies as it is. Now let's see how we can solve this problem. Okay, so a common example of this situation is shown, which you have just discussed above. So it involves the surface of a problem where the symmetry is there and there is a rigid smooth boundary. So let me tell you what this boundary is. This symmetry line can be considered, now since you are only considering half of it, it's called a rigid smooth boundary, and we'll see the meaning of this statement. On this statement, on this particular boundary, because of the symmetry of this problem, it is not expected that any point on this boundary will have a displacement in the x direction. Okay, the reason for that is, if a point over here was expected to move in the x direction, then only that would happen if the loadings were unequal on the other side. For example, on this side the loading is more than this side, and hence there is a tendency of it to move. But since they are exactly the same, you will not have a displacement in this x direction of the mid plane of this. So that is the reason why u is equal to 0 on this boundary. Okay, now the other case on this boundary is, obviously now the x side is taken, so we cannot specify the traction in the x direction. So the traction in the y direction, on this boundary is ty n equal to 0. The reason that is happening, because any point on this symmetry line will not experience a traction in this vertical ty direction. So this is y, this is x, and hence this is true. If the loading was somewhat inclined, then you cannot say this, but because of this particular loading, you can confidently say that there will be no traction in the y direction. Okay, so that is the reason why this second condition is written. So this is called a so-called rigid smooth boundary. There is zero normal displacement and zero tangential traction. Okay, and this is very commonly used in solid mechanics elasticity problems, because many a time symmetry exists and you want to solve only half of the problem or quarter of the problem depending on the symmetry. Okay, especially for computational methods like FEM, etc., you always want to work with half of the domain or one quarter of the domain, just to reduce the computational time is expected. Okay. Okay, now the boundary conditions, as we have seen, they play a very important role, and we must somewhat study a few of them now, just to clarify. One of the things which you should definitely note is the traction definition. Okay, remember Ti of n was defined as sigma ji nj. Remember? If you don't remember, please go back and check the derivation of this. So the traction and the stress are related in this particular form, where n is obviously the outward normal of the boundary. Okay, so outward normal of the boundary is n, and this is how you would proceed. Okay, so you can also have fixed boundaries. I mean, when the boundaries don't move, and then the displacements will be 0 in all the directions or the two directions in under consideration. So let's take one more example. The solid is inside this here is solid. Okay, and these are the two boundaries which I have drawn, 90 degrees. Now consider two elements over here. I'll just rub this. So sigma x would be in this direction. I should write the coordinate axis. Always draw the coordinate axis. People may not think the way you think about the coordinate axis. Okay, they may think that y is somewhere else, especially when it's not very obvious. Sigma y, and this is tau xy. Okay, tau xy. I mean, we have already shown tau xy and yx are same, so we can just draw it like this. Okay. Similarly, on this particular face, you would have sigma y, tau xy, and this is sigma x. Okay. So one of the few things is that the normal is like this on this face. Okay. Similarly, the normal on this face is like this. So there clearly are two separate normals for these two separate boundaries. Okay. So this is a Cartesian Cartesian coordinate boundaries. So as of now, we are only concerned about the Cartesian system and the Cartesian boundaries. We'll take up the polar or the spherical system later on. Right now, we are only concerned about this Cartesian system. Okay. Now, in this particular case, uh, the traction specification can be reduced to a stress specification. You see, there is a very clear relationship between traction and stress. But one thing which you should definitely remember, when you specify the boundary conditions, you should specify either the displacements or the traction. Okay. Yes, once you specify the traction, there can be a relationship between the traction and stress like this, but we should not specify it in terms of stresses. That's the one thing which we should remember, and we'll see that in practice in a few minutes now. Okay. So let's take up. So here life was very easy in this diagram, just because the all the boundaries are aligned with the coordinate axis. Okay, so here it's easy, and we want to now consider another example in which first let's take up one example of this case, and then we'll move to a boundary which is not actually inclined to any of the coordinate system. We want to move to more realistic cases. So let's first take a plate. Obviously, this is y, this is x. Okay. And what we want to do is we want to write the boundary conditions on all the boundaries. So S is the traction which is specified. So this is the example which is given to us. There's a plate in which S is the traction which is given on one boundary, and we have to write the boundary conditions on all of them. So one strategy which I always do is always go with the fixed condition first, just because it's the easiest to deal with. Okay. So which of these faces is fixed? It is this one. On this one, I will write u is equal to 0 and v equal to 0, meaning all points on this boundary will have u is equal to 0 and v equal to 0, means they can neither move in the x direction nor in the y direction. Okay. Next, you should move to a case where the faces are traction free. Okay, there is no traction. So there are two such phases. One is this, one is this. Okay, So let's try to write this and see how it comes out. Let's go with this one first. So the traction in the x direction is equal to 0. Traction in the y direction on this face is also equal to 0. Over here, the traction in the x direction is 0. The traction in the y direction is 0. Now, we also want to find out what are the stresses on these faces. Okay, we specified in terms of traction always, and then find out what the stresses will be. Okay, so let's see first. So we write Ti of n is equal to sigma ji nj. This can be written for a comma j equal to 1 to 2, because we don't have the third dimension in this problem. We can write T1 of n is equal to sigma 1 1 n1 plus sigma 2 1 n2, or this can be written as Tx n equal to sigma xx nx plus sigma yx or tau yx, whatever we want to call it. I'll just write sigma yx. That's ny. Similarly, we will have a T2 of n is equal to sigma 1 1 sigma 1 2 n1 plus sigma 2 2 n2. This means that Ty of n is equal to sigma xy n1 nx plus sigma yy ny. Okay, so let's use these two these two relations and find out what should be the sigma values on these faces. So let's go with this one first. Okay, Tx of n is, so we are trying to use this relation. Okay, so this is 0 is equal to sigma xx. So what is nx? N is like this. Okay, on this face. So let me just use another color. N is like this. So you would have 0 I cap plus minus 1 j cap, and that would mean that n is equal to nx I cap plus ny j cap. This implies nx is equal to 0 and ny is equal to minus 1. Okay, so nx now will be 0 plus sigma yx and ny will be minus 1. This implies that sigma yx or sigma xy, because stress is symmetric, is 0 on this face. Okay, now let's take the other relation, which is this one. Tyn is also equal to 0. That is equal to sigma xy, which we have shown to be 0, and nx was anyways 0. Then you have sigma yy of ny is minus 1 is equal to 0. That implies that sigma yy is equal to 0. So you can say after this that sigma xy is equal to sigma yy is equal to 0 on this face. Now, what is the n on this face? That would be 0 I cap plus 1 j cap. That would mean that nx is equal to 0, ny is equal to 1. So now we want to write this expression for So for this top face, we write 0 is equal to sigma xx, and x is 0, plus sigma yx, and y is 1. So this would make this as sigma yx is equal to 0. And similarly, let's take up this equation now. Ty is equal to, so 0 would be equal to sigma xy, and x is 0, plus sigma yy of 1 is equal to 0. So that would mean that sigma yy is also equal to 0. So for this phase, the stress components are also like this. Now look at the last phase, which is this over here. Over here we will have traction of, in the x. First of all, let's draw the normal. So that would be 1 I cap plus 0 j cap, or nx will be equal to 1 and ny will be equal to 0. So if we substitute this over here, so S will be 0 because the traction in the x direction is given to be S. That's equal to sigma xx 1 plus ny is 0. So sigma xx will be equal to S, and now for this one it would be 0 equal to sigma xy, nx is 1, plus sigma yy is 0. So sigma xy is equal to 0. Okay, so we can write sigma xy is equal to 0 and sigma xx is equal to S for this particular phase. So this is how we have to proceed in trying to write the answer for the stresses for all the boundaries. Now let's consider a case where the boundaries are not actually aligned to the x or y axis like they are in this particular problem. So let's now take that case. Okay, so you have this as the fixed edge. You have traction. Let me draw the coordinate system. That's x, and this is y. This traction is S, and this length is L. Okay, so let's always, as I have said, start with the fixed faces. This one is easy. This should be u equal to 0 and v equal to 0. Start with the traction free, then go to the traction free phase, which is this. What does this mean? Let me just pull it over here. So the traction in the x direction is equal to 0 and the traction in the y direction is equal to 0 because they are traction free phases. Now one can write it in the expanded form like this: sigma x nx plus tau xy, or sigma xy ny, that's equal to 0, and this will be tau xy nx plus sigma y ny. Okay, what is nx and ny? It is basically this nx I cap plus ny j cap. So in this particular problem we cannot write what nx and ny is because we do not know this angle given. If this angle was given, then perhaps we would be in a better position to give an exact value to nx and ny. So we leave this to as it is. Now let's see the third phase. In this one, the traction in the x direction is clearly equal to 0. So that would mean that sigma x nx plus tau xy ny. Now the outward normal in this case is this. That is 0 I cap minus 1 j cap. So nx should be 0, ny should be minus 1. Okay, so once we substitute this over here, you would have tau xy is equal to 0 for this phase. Now let's write for ty of n, that is equal to s. It's a positive s because the direction of y is pointing downwards. That would make it as tau xy nx plus sigma y ny. This implies that s is equal to 0 plus, minus sigma y, because ny is minus 1. So this implies that sigma y is equal to minus s, okay, and tau xy is equal to 0 on this phase. So this is how the boundary conditions are specified on this particular case. Okay. So there are many other examples which one can take, and we will see how more complicated problems can be done when we discuss a few of these problems. But let's see if we can find something interesting right now. That should be okay. For example, if this angle alpha was given as in one of the problems, then you can give a very good answer to what this ny and nx would be. Okay, so that's something which one can try and see how it goes. Okay, so let's move on to a somewhat more realistic case. For example, the interfacial conditions. Okay, this has a wide application in composites, where the reinforcements and the matrix may have some sort of a relationship at the interface. So the interface of the reinforcement and the matrix. Okay, so let's see. If you have, say, a composite like this, which is material 1, sigma ij 1 and ui of 1. Okay, so you have n normal s as attraction, and then this is material 2. Here sigma ij of 2 and ui of 2. Similarly, eij of 2 also using on this. Okay, using the same convention. Now, if it's given that the interface between these two materials is perfectly bonded, okay, so it is a composite elastic. It's one part of a big solid. Or if there is a slip interface, etc. So based on this, one can write the boundaries. Okay, so if for example they are perfectly bonded interface, so then the displacements and attractions will both be continuous at the interface. So if it is perfectly bonded, and this perfectly bonded is a condition, okay, we have to achieve it using a suitable adhesive or whatnot, or some sort of a joining mechanism. But this is, when we say something is perfectly bonded, it implies that both the displacement and tractions are continuous at the interface. So what it means is that, say you have this sigma ij as your strain field, and then ui as your displacement field into, and then you have ui of 1, ui 2. As it crosses the boundary, there must be continuity. So we ensure that in two directions, one in normal and the other in the shear direction. So sigma n 1 is equal to sigma n 2, then un of 1 equal to un of 2. Okay, then the shear stress of 1 will be the shear in the 2, and along the shear directions the displacements. Okay, now for a perfectly bonded, this is the situation. Now one of the facts which you should notice, we said that both the displacement and tractions are continuous, but here it seems we have thrown away the tractions and written stresses. Okay, so please try to find an answer why. Remember, we have done enough of this exercise trying to write the traction in terms of displacement. So please try to write the traction in terms of displacements and then come to this. You have to notice the actual definition is that the displacements and tractions are continuous, not the displacements and stresses. Okay, so this is a end result rather than a starting point. Not this one is the end result. So please arrive at this using the traction stress relationship which we have used. Okay, so if you have, say, the other situation where in this interface which is a slip interface, okay, in this case you have the normal displacement is continuous, but clearly not the shear one because there is slipping between them, and similarly the normal tractions will also be continuous. Okay. How this translates to stress, you have to find out. Okay, so these are the two famous kinds of interfacial boundary conditions which you may encounter in composites. Obviously there are more complicated forms as well, and as you see them you will be able to identify as we move along in this course. Okay, so we want to now, before we begin to formulate the boundary value problem, okay, we want to classify it. So there are problem 1, it is called the traction problem. Okay, so how is this problem defined? We have to find the distribution of displacement, strains and stresses in the interior of an elastic solid in equilibrium when the body forces are given and the distribution of traction is prescribed over the surface of the body. So this is how it looks like. The displacement is specified, the traction is specified over the surface of the body. So S is the surface and XIS is the boundary point. So XIS is the boundary point. Okay. and the fi is the function which is there. So fi can as well be 0. That means that the 0 tractions are specified on the boundary. Okay, so this is the problem 1. And the objective is always the same, to find the displacement, strains and stresses in the interior of a body which is in equilibrium, and the body forces are obviously given, the distribution of traction is specified over the boundary. The problem 2 is the same. We have to find the displacement, strains and stresses in the interior of elastic solid which is in equilibrium, and the body forces given that the distribution of displacement is prescribed over the surface of the body. So this time you will have the displacements specified over the surface of the body. Okay. Okay. Then you have the mixed. Mixed is that you have to again find the displacement, strains and stresses in the interior of the body, given in part of the body you can have the traction specified and the other you have the displacement specified, or even on the same boundary point in one direction you have the traction specified and the other directions, which is the perpendicular direction, you have the displacement specified, so that you do not have a component of one in the other. So in either case, this is three problems which we can classify our boundary value problem into. And obviously, it may be very useful that this is the most realistic case. And now we can, I think, begin by the so-called formulating problem 1, which is the traction problem or the stress formulation. The reason we call it the stress formulation, just because traction can be written in terms of stresses. Okay, no other reason. So let's call this as stress formulation or the traction. Okay, now the motivation is this. You have this elastic solid body, and any point in this, the objective is to find the displacement, strains and stresses. Given that at the boundary you are specified the tractions everywhere on the boundary. Now you remember there are field equations, 6 strain displacement relations, 3 equilibrium equations and 6 for the Hooke's law. Okay, so you had 15 field equations and there were 6 compatibility equations as well, okay, which we were not using, in the sense they were valid but they were not really helpful in trying to convey any new information. Okay, so once that is identified, what we would want to do, because only the tractions are specified at the boundary, we want to convert all our field equations in terms of tractions or stresses only. Okay, so we will see how that can be done. Okay, we'll see how the starting of that question happens, and then let's move on and try to find out how this can work out. Okay. We want to start with the compatibility equation, okay, just because they are valid, right? They are valid, maybe not adding a new information, but they are valid at this point of interest. So let's call that as Eij, comma Kl minus Ekl, comma Ij Eij comma kl minus ekl comma ij plus minus eik comma jl minus ejl comma ik is equal to 0. Okay, so let me just check whether this compatibility equation is correctly written. It is the original form. Of course, we had claimed that many of these terms are actually 0, but we'll just use it nevertheless because it's in the form in which we want, in the sense I, j, k, l. Okay. Okay. Now, what we would do, we would want to use the Hooke's law and substitute the terms in this one. So let's write the inverse of Hooke's law first. That's Eij is equal to 1 plus nu by E sigma ij minus nu by E by sigma kk delta ij. Okay. Okay. Before we do this, as is given in the second chapter, and how do we actually reduce this 81 term system to 6, we do it by contraction, which we have practiced several times now. What we'll do is we'll just put k equal to L in this one. Okay, this will reduce this to a form, and that should be min comma ij zero. Okay. Now we would use this inverse Hooke's law in this and see what we get. One of the things which will happen as soon as we do this is that we will not see any more strains. We'll only see the stresses, and that is what we want because it is a stress formulation. We want to formulate our entire problems in terms of stress. Reason is, if we have the formulation in terms of stress, we can always say at the boundary the stresses will satisfy so and so condition. Okay. And that is why we want to convert this entire problem in terms of stresses, formulate the entire problem in terms of stresses. So we want to write each of the terms now. Let's see how that can be done. Let me first write Eij comma kk. That would be 1 plus nu by E sigma ij comma kk minus nu by E. Okay, so there's a delta ij missing. Okay, that would be sigma mm comma kk into delta ij. And again, due to chain rule, there will be one more differentiation of delta ij twice, but that would be 0, hence I am not writing. So that takes care of the first term. Now let's write ekk. So that is ekk is equal to, we're looking at the second term now. That would be 1 plus mu by E. That would be sigma kk minus nu by E into sigma mm delta kk. Okay, now ekk comma ij can be written as one plus nu by E sigma kk comma ij. Sigma kk comma ij minus nu by E. Then we would have sigma mm comma ij delta kk. Okay. Now let's look at the third term. That would be EIK 1 plus nu by E sigma ik minus nu by E sigma kk delta ik. So let's put this as sigma mm delta ik. Ik comma jl is 1 plus nu by E sigma ik comma jl minus nu by E sigma mm comma jl delta ik. Okay, now let's look at the last term, which is ejk. That would be 1 plus nu by E sigma jk minus nu by E sigma mm delta jk. Okay, now ejk comma ik would be 1 plus nu by E sigma jk comma ik minus nu by E sigma mm comma ik delta jk. Okay, what we'll do now is we'll substitute each of these terms into this compatibility equation, the reduced compatibility equation due to contraction. Okay, so let me put that now. Eij comma kk is 1 plus nu by E sigma ij comma kk minus 1 nu by E sigma mm comma kk delta ij plus ekk comma ij can be written as 1 plus nu by E sigma kk comma ij minus nu by E sigma mm comma ij delta kk. Now then there's a minus eik comma jk, so it would be minus 1 plus nu by E sigma ik comma jl plus nu by E sigma mm comma jl delta ik. Then there's a minus ejk comma ik, that would mean minus 1 plus nu by E sigma jk comma ik plus nu by E sigma mm comma ik delta jk is equal to 0. Okay, so one thing which we can do now is multiply both sides by E. Okay, this would imply that we have 1 plus nu sigma ij comma kk plus sigma kk comma ij minus sigma ik comma jk ik comma jl. Okay, minus sigma jk comma ik. Okay, okay, there shouldn't be a sigma ik comma jl because L was equal to K, so we'll just put it over here. Okay, now this is 1 plus nu this would be equal to nu sigma mm comma kk delta ij plus sigma mm comma ij delta kk minus sigma mm comma jk delta ik minus sigma mm comma ik delta jk. Okay, this implies that sigma ij comma kk plus sigma kk comma ij minus sigma ik comma jk minus sigma jk comma ik is equal to nu by 1 plus nu sigma mm comma kk delta ij plus sigma mm comma ij delta kk minus sigma mm comma jk delta ik minus sigma mm ik delta jk. Okay, so this equation which you have in front of you, what does it represent? It represents the compatibility in terms of stress. Okay, just because you have used the Hooke's law to replace all the strains by the stress. Okay, what we can do now is we can substitute the equilibrium equations. Remember, what are the equilibrium equations? It is sigma ij comma j is equal to minus fi. We want to substitute it over here. So where all can it go? Let's see. So sigma ij comma kk, nothing can happen. Sigma kk comma ij. So let's see how this equilibrium equation can be used. Okay, so there should be at least a couple of terms where I can do that. Yes, I can do it over here. I can do it over here. Okay. Okay, so and then let me see what we can write. So this should imply that sigma ij comma kk. Okay, so as a result of this we can also write, for example, sigma m comma ij is equal to sigma kk comma ij. Okay, so both of these terms we can do. So every time we see a sigma mm comma ij, we will just write it as sigma kk comma ij. Okay, because this we can now write it as 3. Okay, this particular term is actually equal to 3. Okay, okay, so let's see. So sigma ij comma kk plus sigma kk comma ij. Can we see that term anywhere? There it is. So sigma kk comma ij minus sigma ik. So sigma ik comma k is equal to minus of fi, and minus of sigma ik comma jk is equal to fi comma j. This would be f I comma j. Okay, similarly this would be okay, sigma, let me just rub this over here, sigma jk comma k is equal to minus fj. Okay, now sigma jk comma k I equal to minus of fj comma I, and minus of this would mean plus, so this would be plus fj comma I. This is equal to nu by 1 plus nu sigma comma kk can be left as it is. That would be sigma comma kk delta ij, then plus sigma comma ij is the same as sigma kk comma ij. Remember, this particular term and this particular term are the same, so this we would write as plus 3 times of sigma kk comma ij. Okay, then you have minus sigma comma jk. Okay, and what would that look like? Sigma comma ji, right? Comma ij. So this particular term, for non-zero terms, that would be sigma comma ji, because for non-zero values k will have to be equal to I, and this is the same as sigma comma ij because the order of differentiation does not matter. Okay, so we'll write it as minus sigma comma ij. Okay, which we can write as sigma comma kk, sorry, sigma kk comma ij. Let's look at the last term now, sigma comma ik. That would be sigma comma ij, and sigma comma ij can be written as sigma kk comma ij. Okay, so seems we are having a lot of reductions to do. Sigma ij comma kk this can be removed, I guess. Yes, so you will have a sigma kk comma ij, that would be 1 minus nu by 1 plus nu, and what would come with it? So this minus this is actually just one time sigma kk comma ij. Okay, so that we have taken out common already. Okay, now this must be equal to nu by 1 plus nu sigma comma kk delta ij minus of fi comma j minus of fj comma I. This would be nu by 1 plus nu sigma comma kk delta ij, that would be minus fi comma j minus fj comma I. Okay, now what we want to do is, again, we want to somewhat make it easy. So every time you see, we want to sort of eliminate these sort of terms. Okay, this sort of terms, and again that happens by contraction. So what we'll do is we'll put I equal to j. Okay, and this relation should then reduce. Let's see, sigma I comma kk plus sigma kk comma I 1 plus nu by 1 plus nu sigma comma kk, okay, delta I for I equal to j, okay, this will be 1, okay, and that reduces to minus of 2 times of fi comma I, okay, sorry, this should be equal to 3. So can you see that all these terms are actually the same? So we would write that sigma I comma kk 1 plus 1 by 1 plus nu, put a nu by 1 plus nu, sigma, let me just take a minus sign, minus of nu by 1 plus nu equal to minus of 2 times of fi comma I. 1 plus nu plus 1 minus nu by 1 plus nu. Now it is said that after contraction, what we should get, let me do it the other way, we should get sigma I comma kk is equal to minus of 1 plus nu by 1 minus nu fi comma I. Let's see how we can do that first. I think we'll just try out some other way. So until here it seems life is easy. Okay. Sorry, until here life is easy. And now by contraction we have to get this result which we have in green. Let me try that. Every time I get confused, this is what I do and this is what you should do. Put I equal to j equal to p, some unknown number. So that will be sigma pp comma kk plus sigma kk comma pp 1 plus 1 plus nu, nu by 1 plus nu, sigma mm comma kk delta pp minus fi f of p comma p twice. Okay. Now sigma pp comma kk should be equal to sigma kk comma pp should be equal to sigma mm comma kk. Okay, so let me just call it as I don't know, u. So u into 1 plus 1 by 1 plus nu minus nu by 1 plus nu is equal to minus 2 times of fp comma p. See if this works. U of 1 plus nu plus 1 minus nu by 1 plus nu is equal to minus 2 fp comma p. Okay, this gets cancelled. So we have a u times of, hold on, there should be something else. Yes, there is this thing hiding over there which is actually 3. So we should put it as 3 minus
So u into 1 plus nu plus 1 minus 3 nu 1 plus nu minus 2f p comma p. Okay, now this would imply that u of 2 minus 2 nu 1 plus nu is equal to minus 2f p comma p. This should imply, now I'm writing u as sigma I comma kk is equal to minus of 1 plus nu by 1 minus nu into fi comma I. So this shows what we have, what we wanted. Okay, now what is the advantage of doing this? We can simplify one of this term. Okay, so which one term we are looking for? We are looking for this particular term. Okay, so this one we can just use from over here. What would that make this? It would be sigma I j comma kk plus 1 plus 1 1 by 1 plus nu sigma kk comma ij is equal to sigma comma kk, which should be minus of 1 plus nu by 1 minus nu f of m comma m. Then we would have nu by, we would have nu by 1 plus nu, and then you should have a delta ij. Okay, and f of I comma j minus f of j comma I. Let's see, this should imply that we have sigma ij comma kk plus 1 plus 1 by n sigma kk comma ij is equal to minus nu by 1 minus nu delta ij f of k comma k. M comma m can be written as k comma k because there is nothing else to confuse us in this term, minus fi comma j minus fj comma I. Okay, so this is the compatibility equation in terms of stresses. They are called commonly as the Beltrami-Mitchell compatibility relations. Okay, and with no body force, I think it should be very easy to write, because for no body force, this fi comma j and fj comma I terms would be 0. So we can write down this as 1 plus nu as this Laplacian operator. You can just expand this and write it. Please verify that you can write this, that's important. And then you should have so for no body forces we are writing this. Please verify that we actually get this. All you have to do is just ignore the body forces and then expand it with I and j. So I'm just writing the final scalar form. And lastly, remember even in the last time when you put k is equal to L in the compatibility equation, you were getting 6 equations, and right now you also have 6 because you have done that contraction. So these are the 6 Beltrami-Mitchell compatibility equations. Okay. So there is obviously a way to combine these results and prove that they are actually only 3 equilibrium equation. Okay. So that's something which one can do. So this is the formulation of your elasticity problem. So what it means is that if you have any solid, the interior point of it will satisfy these equations, these 6 equations. And hence, if you want to apply boundary conditions, say at a boundary point like this, then you will put the suitable sigma x, sigma y, sigma z, and tau xy, tau xz, and tau yz on that particular point. That value you can take. So that's how that makes it very easy. So the next and the obvious thing to do is to do the displacement formulation. As you may have guessed it right, we have to formulate our problem in such a way that we only see displacements, okay, not stresses or tractions. That this you would automatically do when you have a displacement boundary condition. If you have the displacement boundaries, or you have the so-called support specified, then you will formulate your entire problem in terms of displacements. So for this, what we do is we start with the Hooke's law. Sigma ij is equal to, what would that be? Lambda. Let's just check before, because one small error means a lot of time lost. Okay, so sigma ij is lambda ekk delta ij plus 2 mu eij. Okay, now we start with the Hooke's law for isotropic, linear elastic isotropic solid, and the objective is to get rid of all the stresses everywhere, okay, and convert the final thing only in terms of displacements. So for that, we start with writing the strain displacement relations, and then we'll see how the strains and stresses can be eliminated in the Hooke's law. So the strain displacement relation, as we know, is Eij is equal to half of Ui comma j plus Uj comma I. Okay, and let's do that substitution. Or separately, let's just write Ekk is equal to half of Uk comma k plus Uk comma k. That's actually equal to Uk comma k. So let's do this substitution. This implies that sigma ij will be equal to lambda ekk is Uk comma k delta ij, okay, plus mu into 2eij would be ui comma j plus uj comma I. Okay, so this can be written in terms of the scalar expressions as well. So let me just write a couple of them, though they are not directly relevant over here. So sigma x would be equal to lambda into dou u by dou x plus dou v by dou y plus dou w by dou z plus 2 mu dou u by dou x. Let me write a shear term as well, tau xy. That would be equal to, so for this what you will do, put I equal to 1, j equal to 2 in this one. Okay, then we would get tau xy. That would be equal to mu of dou u by dou y plus dou v by dou x. And similarly 4 more terms. Not writing, but it's easy to see that. Okay, so now we would want to use this relation in the equilibrium conditions. Okay, so let's write what the equilibrium condition is. That sigma ij comma j plus fi is equal to 0. we want to use this in the equilibrium equation. So sigma ij comma j can be written as equal to lambda. So we'll just look at this equation. Okay, so that would be lambda of let's just do it over on this side. So sigma ij comma j, that would be equal to lambda into delta ij u k comma kj plus, I'm not writing the differentiation for delta because that would be 0, plus mu u I comma j j plus u j comma ij. Okay, so this is the sigma ij comma j, and let's see how this can be written. So this implies that sigma ij comma j is lambda delta ij u k comma kj plus mu u I comma j j plus u j comma ij plus fi is equal to 0. Now we want to do a few things over here. First is that we can say that for non-zero deltas j will have to be equal to I, so it will be k minus k comma ki plus mu into u I comma j j plus u j comma ij plus fi equal to 0. This would imply that we can write mu into, so my u and mu seem similar when I write, but I hope you can clearly see, because u will always come with a subscript and mu will never come with any sub or superscript. Okay, so mu into u I comma j j plus lambda plus mu u j comma ij plus fi to 0. Okay, because this term is the same as this term, because the order of differentiation does not matter. So that can be written as mu of u I comma kk plus lambda plus mu u of k comma ki plus fi equal to 0. Okay, so this is what, this is the equilibrium equation in terms of displacement. You do not see any stresses anymore, nor do you see strains. So this is called the Navier's equation or Lame's equation, just like the other one was called Beltrami-Mitchell equation. And this you can write as mu into square in terms of the Laplacian. So if you do not exactly know how this Laplacian is taken, please check up any basic mathematics book and you should know what is the Laplacian of a vector. Okay, here u I have written with a vector sign, so you should note that. And then you would have the gradients of a divergence of, okay, so this is the vector form of this Navier's equation. Okay, these are three separate terms and this three separate equations, and this has been vector form of this equation, so they can easily be written in the scalar form. So that would be mu into Laplacian plus lambda plus mu 2 by 2x plus 2v by 2y plus 2w by 2z plus fx is equal to 0. Then you have u v plus lambda plus mu So the Laplacian is just for your information. Okay, so this is the displacement formulation. Now the way to solve is, and we will see at least one part of it. For example, the traction formulation. How do you actually solve it? This is solved as using something called the stress function. We will see this in our course. And this displacement formulation is done by something called, no surprises, displacement function. Displacement function. Both of them are so called using a single potential. And this is something which is outside the scope of this book, the displacement formulation, but stress function we'll be seeing quite often. So we'll be learning about the stress formulation more, but it should be easy the way you see it. Okay. Okay. So before we sort of close this particular topic, there are a couple of things which we have to learn. And those are, the first is the principle of superposition. Remember I think in the last class or lecture before, I had said that there are two reasons why the linear elasticity is popular despite so many decades or even a century, and it's still very commonly used and very widely applied. There are two reasons for it. One of the reasons is principle of superpositions. Let's try to see what it is and what is the motivation behind it and how is it helpful. So this particular, you see that you have a lot of linear equations appearing. Okay, because of the small strain theory, you only have linear equations. So all elasticity equations which you have, all field equations which you have are linear. Okay, so linear meaning any unknown enters the equation linearly. So you can write, say, L phi is equal to L phi 1 plus L phi 2 and so on. Okay, if phi is equal to phi 1 plus phi 2 plus so on. So this is what linearity means. And all field equations which you have is linear. Please verify this. Do not proceed ahead without verifying that all the field equations. What are the field equations? Strain displacement, Hooke's law, and the equilibrium equations. They are all linear equations. So please verify this moving ahead. Now the principle of superposition is quite simple. It states that for a given problem domain, if the state, let me just write it, it's so nice that it wouldn't make any sense if it's not written. For a given problem domain, if the state sigma ij1 ij ui is a solution to the fundamental with prescribed body forces Fi of 1 plus tractions Ti of 1. And the state sigma ij of 1 eij of 2 sigma ij of 2 ei of ui of 2 is a solution to the fundamental elasticity equations with body force Fi of 2 and surface fractions Ti of 2 okay. Two, then the state sigma ij of 1 plus sigma ij of 2 comma eij of 1 plus eij of 2 comma ui of 1 comma ui of 2 will be a solution to the problem with body force Fi of 1 plus Fi of 2 with tractions. Okay. So for a given problem domain, if the state sigma ij1 eij1 ui of 1 is a solution to the fundamental elasticity equations with prescribed body forces Fi and surface tractions. So if you have this as 1, sigma ij of 1, eij of 1, ui of 1, okay, and this is a second problem, okay, for the same domain, for a given problem domain, okay. The domain doesn't change, it's the boundary conditions which change. Now in second situation, say your loadings are like this, and then you have the solution, meaning any point on this inside this solid has this stress and strain and displacement field. Then if you have a combined loading, okay, then this any point inside this solid will have the stress as given by this and strain as given by this and displacement as given by this. Okay, so this is the principle of superposition. How is this helpful? Very simply, if you have very complicated boundary loadings, okay, boundary conditions are very complicated, you can break them, your problem down into 2, 3, 4, 10, 15, 20, 100 smaller problems like this, okay, and then individually solve those smaller easier problems, okay, find the stress and strain due to those individual problems and then just add them up, and that would be the solution to your very complicated loading problem. So this is the advantage. You can break down your problem into any number of easier problems and just solve each one of them simply and just add your answer for stress, strain or displacement at any given point. This is the one of the reasons where linear elasticity is so popular, because you do not have this advantage in plasticity, in viscoelasticity or any other such kind of a behavior. Okay, so principle of superposition is one reason why linear elasticity is so popular. Okay, we'll see this in action in some of the problems, but I hope you can get the gist of it. Okay, we also want to discuss another concept which perhaps you may be knowing from your earlier knowledge. That's called the Saint Venant's principle. Why is it coming like this? Okay. So I'll just write the statement first and then we'll see, understand it. The stress, strain, and displacement fields caused by far away from the loading are approximately the same. Okay, let's see this. So if you have a loading applied on this by P, you have a statically equivalent loading P by 2 and P by 2. You have a statically equivalent loading P by 3, P by 3 and P by 3. Okay, so these are all statically equivalent loadings. Okay. So let's read the principle. The stress, strain and displacement fields caused by two different statically equivalent force distribution on parts of the body far away from the loading are approximately the same. Meaning, if you want to find, say, the stress, strain or displacement at this point, which is far away from the boundary, in all the three situations, statically equivalent loadings, your answer would approximately be the same. Okay, so that's the principle, and this is also very helpful, that sometimes it is more easier to work with a statically another statically equivalent loading, and then you can do that and be assured that the answer which you get of your problem will be valid as long as the point of interest is away from the boundary. If it's not away from the boundary, then you can have the so-called boundary effects. Okay, there'll be some concentration over here, but as soon as you, the whole point is, as you move away from these, then the boundary effects die away, and hence the approximate answer of the stress or the strain at this point will be approximately the same. So this is also a very powerful idea, Saint Venant's principle, and it's used in problem solving. Okay, when the solution is not as easily found out for a given problem, what you can do is you can change the boundary conditions to an equivalent loading, like in this case, and then see how you can proceed with this problem. Okay. So there are some discussions in your textbook which are there for this topic and the topics which follow, which is the solution strategies. I request you to do that yourself, because it will be best done if you read it yourself, and we will be moving on to the next topic of strain energy density in our next discussion. So thank you.